Hello, everybody. Welcome to a new episode of the Dissenter. I'm your host, as always, Ricardo Lopes, and today I'm joined by Dr. Paul Halpern. He is professor of physics at St. Joseph's University in Philadelphia. He is the author of several books, and today we're focusing on his latest one, The Allure of the Multiverse, Extra Dimensions, Other Worlds, and Parallel Universes. So, Paul, welcome to the show. It's a big pleasure to everyone.
My pleasure too. Thank you for having me on your show, Ricardo.
So let's start with this then. I know that in the book you go through a little bit actually of the history behind the idea of the multiverse, and you of course focus mostly on physics, but you also talk about the ideas of some philosophers, for example. So do you know how old is the idea of the multiverse actually?
Well, it's interesting because the term multiverse goes back to William James, who was a writer and also kind of an early psychologist, and he talked about the psychological idea of a multiverse back in the 19th century as kind of a morally ambiguous universe, that a universe that was neither good nor evil and was pretty much ambivalent to whether someone is good, someone is evil. So he called it kind of a moral multiverse, but that's just a term. I don't think he meant that in the sense of parallel universes. And the idea of parallel universes in science really took off in the 1970s and 1980s. And especially in this century, in the 21st century, the idea really became popular. But going all the way back to the people like Giordano Bruno, the Italian philosopher, that's when people start talking about many worlds out there, worlds that might be similar to Earth. And Bruno, of course, famously was burnt at the stake for writing that there are an infinite number of worlds out there, and some of those could be, inhabited and like Earth. And he speculated about this, and that was considered heresy, blasphemy by the Roman Inquisition. And, sadly, he was killed by the Roman Inquisition for that heresy and other heresies. And then around the same time, Galileo, who was a little bit higher placed, he had more connections, so he wasn't, luckily, he wasn't executed, but he also speculated about, many worlds out there. And then in the 19th century, based upon Newtonian physics, Newtonian determinism, people started figuring out that if you have a finite number of elements, a finite number of possibilities, but an infinite universe, eventually all the combinations would start to repeat themselves. So just like if you're playing the game of chess, eventually you run out of moves and would repeat the same moves. There are not an infinite number of moves in chess. Similarly, if you had an infinite universe but a finite number of elements and a finite number of possibilities, eventually you would have something like Earth recreated. And the philosopher, well, the revolutionary Louis Blanqui in France, while he was imprisoned in a fortress for revolutionary activity, speculated that there might be many, many copies of Earth out there, that some of them might be exact, some of them might be inexact, and maybe some of the things that play out on Earth would happen in some of the other universes, such as French Revolution and so forth. So it's kind of interesting to think about this. But now we know that the universe is expanding and accelerating its expansion. So, and it might be that there is a duplicate Earth out there, but it would be so far away from us, it would be well beyond the possibility of observation, well beyond the observable universe, because the sheer probability of creating something that's exactly like Earth would be so minimal that it would take far longer than the time length of the Big Bang, and far greater than the size of the observable universe to recreate something like that. So it's pretty much impossible.
So one idea that you mentioned there, the fact that people at a certain point notice that if there are a limited number of possible arrangements of matter, then if time is infinite, then eventually the same configurations would repeat themselves over time. That's actually something that comes around also in Nietzsche, right? And the idea of the eternal return. Because I guess that in that aspect, he was influenced by some physicists back in the 19th century, right?
Yeah, so Friedrich Nietzsche, the German philosopher, um, came up with the idea of eternal return. And he, unlike Eastern philosophers, he talked about an exact repetition of history.
Right.
So he imagined that his life and all of its pain and suffering and some joy, mostly pain, a little bit of joy, would repeat itself sometime in the future, just based upon the idea of chance reoccurrence. So, for any kind of game with finite elements, I mentioned chess, but also a game of tic-tac-toe with X's and O's, eventually you just run out of moves. And tic-tac-toe, if you're familiar with it, has a square, has nine elements in a square with X's and O's as the only possibilities. And it can be a boring game if you play it long enough because you repeat the same moves again and again. And similarly, Nietzsche thought that his life would repeat itself. But if we estimate how long it would take for Earth to repeat itself, it was, far, 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 almost unimaginably far longer than the history of the universe. So it's incredibly unlikely, as people like Nietzsche's contemporary Ludwig Boltzmann pointed out. Boltzmann talked about the idea of the arrow of time and increasing entropy. People said, "Hey, wait a minute, things could randomly come together again," but the estimate of that happening is just incredibly improbable. So uh, normally we don't have to worry about it.
Mhm. But let me just ask you one question, since you mentioned Giordano Bruno there earlier and also Galileo, and now we're talking about Nietzsche. Because if I understand it correctly, for example, Giordano Bruno was talking back then in the 16th century or so about there being other worlds, but by worlds, I guess he was referring mostly to planets, other planets like Earth out there. I mean, but so, and if those people are mostly talking about other worlds in our universe, or in the case of Nietzsche, inside of our universe, things repeating themselves over time, that isn't exactly the same thing as a multiverse, or is it?
Yeah, that is an excellent point. And that's why I say the modern idea of a multiverse, actual multiverse, started in the 1970s, when you had Bryce DeWitt popularizing the idea of Hugh Everett of what's called the many worlds interpretation of quantum mechanics. And
Mhm.
that's a name that DeWitt almost coined. He said many universes, but it became many worlds. And then Brandon Carter took that idea and turned it into the variation of it into the anthropic principle. And then later other scientists took that idea to try to explain fine tuning, and I'm sure we'll talk about that later. But that was an actual idea of something beyond the physical universe. But our scope has expanded over the centuries. So of course, at the time of Pythagoras, the time of the ancient Greeks, no one imagined that there was really anything beyond Earth. And maybe the Pythagoreans talked about a central fire, but they talked about 10 objects, including the celestial sphere, which was, the dome of stars. And that was kind of considered something fixed out there, not something with, unlimited objects, but something that was just kind of this fixed dome, a fixed element, and these planets. But we had no idea what the scope of the galaxy was, let alone the universe. And then, of course, in the time of Galileo and Bruno, we started to think about other stars, other planets, but they weren't known yet. And it was only in the 1990s, believe it or not, that astronomers detected the first exoplanets beyond the solar system. And that was, when we got to confirm that hypothesis finally, Bruno's hypothesis, that there are actually other planets around other stars. And now most astronomers think that there are trillions of planets out there, just based upon the ones we've found so far, the thousands of ones we've found so far. If you extrapolate, there are likely planets around most stars. So we can talk about trillions of planets out there. But then within the last 100 years, believe it or not, that's when we discovered other galaxies. It was only really in 1926 with the observations of Edwin Hubble that we showed that the Andromeda Nebula, as it was called, it was thought to be a gas cloud, was really an object outside of our own galaxy. And that resolved what was called the Great Debate over whether or not the Milky Way was the only object, give or take a few things in the periphery, or if there are numerous galaxies out there.
And how do physicists themselves think about the multiverse? And are there different conceptualizations of what the multiverse might be among physicists?
Yeah, so there are many different multiverses, which can be a little bit confusing. And none of them are really like the cultural idea of the multiverse, which you can
Yeah.
also talk about, which is the multiverse in movies. So everyone imagines in movies, you know, you wake up and you go through a portal and you see a near identical version of yourself, or you see, a superhero that has a different origin story, like a different Spider-Man or a different, you know, different version of Ultra or whatever, like different superheroes. But in physics, the multiverse ideas are confined to either something having to do with the very small or something having to do with the very large. So either a quantum multiverse or a cosmological multiverse. And the quantum multiverse is usually called the many worlds interpretation of quantum mechanics. And that was developed by Hugh Everett III, who was a student of the great American physicist John Wheeler, who I had the pleasure of meeting before he passed away. Very interesting fellow. And Hugh Everett proposed the idea that when you take a quantum measurement, you, the observer, do not affect the measurement. You do not influence the measurement. So then the question arises, how come you get an exact result? Whereas we know in quantum physics, you have a blending of possibilities before the measurement is taken. How do you get an exact result when the measurement was taken? And the old idea, the orthodox idea, is that the measurer collapses the wave function down to one possibility, like knocking over a stack of cards and collapsing it down to a single pile. Well, Everett's idea is that the measurer does not affect anything. Rather, the measurer sees all the possibilities, all the different outcomes at once. Well, how can that happen? Because the measurer's conscious record says, I see one observation. So that must mean that the measurer's consciousness branches out into multiple possibilities, and each version of the conscious observer sees a different value or a different outcome of the measurement. So there's a branching of human beings that matches the branching of quantum outcomes. And that all matches up with a universal wave function that never collapses, but there's all these possibilities out there in different enclaves of the universe. So that gives you parallel universes. So that's a quantum idea. In cosmology, it's the possibility of other bubble universes out there aside from the Big Bang. So aside from our own Big Bang, that there are other universes expanding out there just beyond the range of observation. And that, for some people, is more palatable because that's not something that's happening all the time. This is something that happens, with a cosmogenesis event, a universe creation event. And it almost seems, in a way, logical if our universe is created in a relatively easy way through, the observable universe created in a process called inflation, that maybe inflation happens, elsewhere in reality.
And so those are the main reasons why theoretical physicists have theorized about the possible multiverse. Is it for explain with the idea of explaining those aspects of our reality?
Yes, well, we want to explain the observable universe, and we
Mhm.
want to explain the observable results from quantum measurements.
Yeah.
So we know that when we take a quantum measurement, we get, if we repeat the measurement, we might get different outcomes, but if we repeat the measurement enough times, we can map
Mhm.
out the probabilities of those various outcomes. So we know that there's a certain amount of chance. We know that there's a certain range of possibilities. We know that we don't always get the same possibility. And we know um, that the results uh, can only be precise for certain parameters because of Heisenberg's uncertainty principle, that we can't measure position precisely and the momentum precisely at the same time. So these are things we know. The question is how to explain it. And there are many different ways to explain quantum measurement. Similarly, we know that the universe on the largest scale is very even, very regular. If we look in one direction, we see pretty much the same number of galaxies as in the complete opposite direction. If we look and measure the cosmic radiation background, the temperature of it is very, very close to the same in all directions. There's slight variations. So the question is, how do we get such uniformity? Is it just a coincidence? Or is there some reason that the universe smoothed out in the beginning? That led to the idea of inflation. And then it turns out that inflation is pretty easy to produce in Einstein's general theory of relativity by just having the right energy configuration, the right energy setup. So Andrei Linde, the Russian-born cosmologist who's now at Stanford University, came up with the idea of an eternal inflation, which is that this happens repeatedly. But I should say that the idea of the multiverse really became popular when people started grappling with the idea that the cosmological constant of the universe, which is a kind of anti-gravity parameter that's causing the universe to slightly accelerate over time, um, seems very large by one calculation, calculating the quantum energy background. So if you look at empty space, it's not really empty. It has particles that are popping in and out of emptiness. And if you add up the energy of all those particles, you get something that could be called the cosmological constant. And let me explain what the cosmological constant
Mhm.
is. When Einstein developed his general theory of relativity, which is how space and time create gravity through their curvature,
Yeah.
he realized that he wasn't getting stable results. He was getting results that would either contract or expand. And it was when he developed that was before Hubble's proof, as it turns out, that the universe is expanding. And he thought he made a mistake. So he added the cosmological constant as a stabilizing term, which kind of pushes the universe outward to stabilize it against gravity to make it a steady universe, a static universe. But then he dropped that idea. He said it was a big mistake, that he shouldn't have even introduced it. But ideas tend to persist. And in 1998, two teams of cosmologists used observations of the universe to show that not only is the universe expanding, it's accelerating in its expansion. So something is pushing it out faster and faster over time. And that must be something which sometimes is called dark energy, but you could also use a cosmological constant as a way of modeling that dark energy. That cosmological constant turns out to be very, very small, because if it were big, it would have affected the development of stars, galaxies, and so forth. It would have made it impossible for structure to form. So it's this really, really minute cosmological constant. So you don't feel it until billions of years into the history of the universe. So the first 5 billion years of the history of the universe, you don't feel this anti-gravity push, and stars can form, galaxies form, Earth forms, everything forms just nice. But then later in the history of the universe, suddenly you start feeling this outward push, and the universe starts to speed up in its expansion because this cosmological constant term is small. But people in quantum field theory calculate the cosmological constant based on the energy of empty space, and they say it must be huge. So the question is, why in reality you have a small cosmological constant, but really based on quantum field theory you should have a large one? And the answer that some people have is that maybe the universe is really a multiverse, and that you have all these expanding universes out there, and each of them has its own cosmological constant, and that some of them are enormous and some of them are moderate. And we happen to be in an outlier. We happen to be in the very, very odd, strange universe that has a tiny cosmological constant. So, so we're just in this really bizarre universe that has a small cosmological constant. But it's lucky that we are, because that's the only way stars can form and galaxies can form and life can form. And that's why we're here, because we happen to be in a universe with a tiny cosmological constant. And all the other universes with the large cosmological constants never form structure. So there was no one there to say, hey, we're in a universe with a large cosmological constant.
So you mentioned Einstein there, and of course you theorized about the space-time continuum and about a fourth dimension of reality. Does this idea of going above the three dimensions also connect in any way to the idea of the multiverse, or not?
Well, the idea of dimensions is very interesting. Dimensions is a little bit of a strange concept, because we know that there are three tangible physical dimensions. If we can, walk north and south, we can walk east and west, or we can jump up and down. Those are the three ways we can move. So those are the physical dimensions. But then at some point, people started saying, even in the late 19th century, that time has a quality that resembles a dimension, because you can imagine things changing over time, just like they might be different in different directions in space. And that idea was solidified when Hermann Minkowski in 1907 said that Einstein's special theory of relativity was best developed in four dimensions. And finally, after a few years of saying, oh, four dimension is kind of an abstract concept and not really liking it, Einstein adopted the fourth dimension and used it in his general theory of relativity. So that's pretty well accepted. But around the time that Einstein proposed general relativity, a mathematician, Theodore Kaluza, who was in East Prussia, part of Germany, German Empire, wrote to Einstein and said, hey, wait a minute, maybe you can add another force to your theory, electricity and magnetism, which we call electromagnetism. by adding an extra dimension to your theory and having a fifth dimension that we don't detect, but still comes into the theory. So that's the Kaluza idea of a fifth dimension. And later, someone named Oscar Klein connected it with quantum physics. So now we call that Kaluza-Klein higher dimensional theory. And Klein proposed the idea that the higher dimension was kind of curled up into a very tight circle, kind of like if you look at a piece of spaghetti or a piece of pasta, and you look at not the long part of it, but we look at the radius of it, it's very, very tiny. So if you were observing a piece of spaghetti from a great distance, it would just look like a one-dimensional object. It would look like a straight line.
Mm-hmm.
You wouldn't be able to tell that it has a thickness. And similarly, in the Kaluza-Klein picture, the higher dimension, the fifth dimension, is curled up so tightly into such a tight little circle that we never really detect it. That's impossible to detect. Well, if you look later in the history of physics, string theory was developed starting in the 1980s as this idea that particles are not really particles, but they're energetic strands that are vibrating, and their vibrations create the particle categories. But mathematicians discovered that string theory does not mathematically make sense. It's mathematically inconsistent unless you put it into a 10-dimensional theory at least. And so you need to add not just a fifth dimension, but you need to add 6 more dimensions beyond space and time. So, so you have 10 dimensions, and in a related topic called supergravity, people like Eugene Kremer and Bernard Julia in France developed the idea of spontaneous compactification. And I think that was developed in the late 1970s, this idea that all the other dimensions would collapse and you would only see 4 of the dimensions, but the other dimensions would just, become crushed into something that's undetectable. And other physicists found that there are many, many, many different ways that this collapse of the higher dimensions can occur, and many different possible geometries for the higher dimension once it's collapsed. It turns out to be 10 to the 500 power possibilities for this kind of collapse into 10 to the 500 power types of geometries. And you can think of those geometries kind of like pretzels, not just rings, but or donuts, but all these different twisty pretzels, and imagine 10 with 500 zeros possibilities. And each of these can lead to its own universe model, its own physics. And some physicists talk about, 10 to the 500 possible universes out there, each with its own type of what we call internal geometry. Internal meaning that you don't really see it, as opposed to external geometry. So that's yet another idea of the multiverse, is that to try to explain why we're in one particular type of universe, but there's all these other possibilities out there, 10 to the 500 other possibilities out there, which is very, very perplexing. And that's how dimensions comes into the picture of the multiverse models.
And so these universes with different configurations, should we expect them to also have different laws of physics?
Yeah, so they would have not necessarily super different laws, like you might think, if you know naively physics, you say, okay, force equals mass times acceleration, something you learn in basic physics. And then, you wouldn't have like force is mass to the third power times acceleration cubed. But you might have different constants, strength constants for the forces. So we have all these parameters in physics which tell you how strongly particles can interact with each other. So, for example, if you have, you know, two magnets, like two refrigerator magnets or bar magnets, and you hold them 1 meter away from each other, you know how strong the attraction will be. Well, maybe in another universe, they would have a much stronger attraction to each other. Maybe in a third universe, they'd have a much weaker attraction to each other. So in one universe, like you might have a refrigerator and you want to put a magnet on the refrigerator, with your favorite football team or something like that. You put it on the refrigerator and it just never sticks because the magnets are never strong enough. And then in another universe, you get a magnet for your favorite football team. You put it on a refrigerator, and then that football team does terribly. Like they keep, losing. Like, oh, I'm going to support another football team. You try to take the first magnet off, but it's impossible because it's stuck on there forever because the magnetism is so strong. So, you know, we're lucky we're in a universe where you can take refrigerator magnets on and off, and they'll stick as long as you want to. But then if you want to take them off, you can take them off.
But let me just ask you one more question about dimension. So, is it possible in any way to, to test that out empirically, to detect them empirically, or is this something that we just are able to figure out mathematically?
Well, with these unseen dimensions, the whole theory is designed so that these dimensions would be undetectable. But then, of course,
Mm.
people will say, well, then how do you prove it? Well, then you try to look for what are called low energy ramifications. So string theory operates, it lives on a very, very high energy scale. So if you want to see string theory, don't really have the possibility of creating colliders on Earth or even in the solar system that would be strong enough to produce those ultra high energies. But then people say, well, maybe you can see a slight change in the results due to the higher dimensions. So there are theories that predict you would see a slight difference in the outcome of a collision experiment due to the fact that there are more dimensions in space. So those are the things people are trying to
Mhm.
test for, these subtle differences. And so far, these haven't been found. That would be Nobel Prize winning material if you could show that a collision experiment, you get a difference that's significant enough to show that some of the energy, for example, escaped into a higher dimension.
And when it comes to the origins of our own universe and the Big Bang, which is something you referred to earlier, what is the most accepted explanation for the origins of our universe, or the way that the Big Bang occurred or played out?
So most physicists don't talk about what happens before the Big Bang because,
Mhm.
um, as people like Stephen Hawking proved in the 1960s, the actual Big Bang event would be a singularity.
Yeah.
So nothing would be detectable before then. Now, that said, there are other theories about cosmic cycles, that there were other cycles of creation. But the standard Big Bang theory is that it's a singularity, that time began essentially at that point. So we
Mhm.
can't really talk about before the Big Bang. And then space came into existence during the time of the Big Bang. Time came into existence. And then the universe immediately began expanding. But then at this point, there was a certain amount of energy in the universe, a certain amount of energy background. And one thing that was found in the early universe is something with a technical name. It's called a scalar field. And a scalar field sounds like, something very mathematical, but in reality, it just means that you have a map of energy that's different from point to point. Kind of like if you were going mountain climbing and you wanted to find out which were the highest peaks, which were the lowest peaks, and what would be the best way to climb up a mountain, you might have a topographical map. And that topographical map would tell you the elevation at every point. So it might say, okay, this point is 500 meters high. This point is 1,000 meters high. This point is more. This point is less. And then you can plan your walk and your hike up the mountain based on the topographical map. Well, if you look at the early universe right after the Big Bang, you could map out its energy, and that would give you what we call a scalar field. And if that energy has a certain profile, meaning it has a certain level, and that level persists for a while and slowly changes over time, then that bump in energy causes expansion, super rapid expansion at that particular point in space. So if you have a certain energy profile that's flat for a certain period of time, meaning it'd be kind of like you have, you climb up a mountain and then you have this flat plateau where things are pretty much level, that triggers the universe, space in the universe, to start expanding really rapidly. It's just a result of Einstein's general theory of relativity, which says that space expands depending upon what's in it, what mass is in it, what energy is in it. So space starts to expand rapidly. That stretches out that part of the universe, and that's called inflation. And that happens super rapidly. And suddenly, when things expand enough, the universe no longer sits in that energy zone, it's no longer subject to that scalar energy field, which has evolved slowly over time, and that you no longer have inflationary period. That enormous amount of energy created by that super rapid expansion turns into all these particles. So all the particles that we see today, light particles called photons, the particles we know as electrons, the quarks, and this whole zoo of particles is created at the exact moment that inflation stops, and all this energy turns into matter, following E equals mc squared. Energy is matter times the speed of light squared, as Einstein said. So then that's when the physical universe with all of the particles is created. But as Andre Linde said, this might happen in other parts of the early cosmos, creating other inflationary events and other universes, and that's where you get the multiverse picture.
So, I mean, is that idea that we sometimes see or read about in popular science publications, where, I mean, if a multiverse is real, it is usually depicted visually as different bubbles or different spheres, and then we read that basically what could have happened is that two of them, or perhaps even more, collided, and when they collide, they create a new universe, or they provoke what would be a big bang, and a new universe is created from that. I mean, does that have any support in actual physics or not?
Well, there are ideas of higher dimensional planes
Mm-hmm.
called membranes,
Yeah.
or branes for short, colliding along a higher dimension. That's a different idea that was
Hmm.
proposed by Neil Turek, Paul Steinhardt, and others uh, around 2000.
Yeah.
And that's called a cyclic cosmology, and that's an alternative to inflation. In inflation, the bubbles expand and they could collide, but when they collide, they don't really create a new universe.
Okay.
They maybe create a little scar. So when two universes collide, they might create some disruption in matter and energy, and that theoretically could be seen in a kind of rings, scar-like rings in the cosmic microwave background. And scientists are trying to look for these rings that are relics of early collisions between us and another universe. So that is one way of trying to physically prove the existence of a multiverse.
Hmm.
So in my book, I interviewed Hinyana Pirals, who's a researcher at the University of London, who her team is trying to look for evidence of bubble collisions in the early universe, and also their latest project is to try to simulate this computationally.
And do black holes connect in any way to the multiverse or not?
Well, there is a theory by Lee Smolin,
Hmm.
uh, a physicist, that black holes uh, they 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 are known to be extreme events in the universe, and if you look at standard general relativity, we say that the more mass you have concentrated in a point, the more space-time warps. Well, for
Yeah.
black holes, you have an infinite warping. So it creates what can look like a tear or a hole in the fabric of space-time. And there are ways to mathematically connect the black hole with another part of space
Yeah.
and create a kind of what could be a connection with another part of our universe. And some speculate that it could create a new universe, as Lee Smolin called it, a baby universe, and that this baby universe could grow up into a big universe and then create more black holes. And he has this idea of survival of the fittest, where the universe that creates the most black holes is evolutionary fitter than other universes, because it also creates more stars and more planets and more likelihood for life. So that's a really interesting idea, but that's not really the thrust of uh, most researchers who study the multiverse. It's more of an idea of one researcher.
Mhm. And does the science and philosophy of counterfactuals have anything to do with the idea of a multiverse?
Well, yes. So in philosophy, we can speculate upon all the possibilities that are out there, and that was done all the way back to people like philosophers like Leibniz. So Leibniz talked about all the possible universes out there, that he talked about the divine or God,
Yeah.
thinking about all these other possibilities. But of course, God is, as he would say, perfect in his wisdom, and chose from all these among these other possibilities the best possibility for us, the best of all possible worlds. But he imagined all these other worlds out there, where Earth was brutally hot and unpleasant, and food was unappetizing, and people were, you know, uh, these unthinking beings. But in his wisdom, he said, okay, we want a world which is pleasant, has nice climate, has nice oceans, and has people who are kind of a little bit like, a little bit like the divine because they can make choices and so forth. So Leibniz kind of talked about this idea of the best of all possible worlds. And the writer Voltaire famously satirized this idea with his character Candide. So as his novel Candide, where he had a character named Pangloss, who was a philosopher who, no matter what happened, there could be an earthquake. Um, in fact, I think he talked about the great earthquake in Lisbon, and this horrible earthquake. And he said, well, it must be the best possibility because God meant us to be in the best of all possible world. So even if there's all this suffering, it still works out for the best. And Voltaire thought that was very amusing, that a philosopher would say anything is always the best outcome.
Mhm. So one of the questions that you also explore in the book is how explaining why the universe is habitable as something to do with the idea of the multiverse. So what's the connection there, or the possible connection?
Well, this was an idea called the anthropic principle,
Mhm,
developed by Brandon Carter, who was someone he was at Cambridge. He was a friend of Stephen Hawking, and Cambridge was this really hot area for cosmology. It still is, but in the 1970s, Cambridge and Princeton were two of the best places to go. At Princeton, you had John Wheeler. At Cambridge, you had people like Hawking and Penrose,
mhm,
and Brandon Carter was also there. And Carter also spent some time at Princeton, so we got to know John Wheeler, and he found out about Hugh Everett's idea of the many worlds interpretation.
mhm,
So that got Brandon Carter thinking about the multiverse, although it wasn't called as such. And he thought, well, there's all these questions, cosmology, about parameters, like why certain physical parameters should have certain values. And that's called the fine-tuning problem,
mhm,
because if the strength of electromagnetism was different, you wouldn't have, for example, atoms, being stable. If you had, for example, the charge of a proton being slightly different than a charge of an electron, then the atoms would collapse. So there are all these coincidences in the universe, things that if you change slightly, the universe would not be suitable for life. And Brendan Carter said, hey, wait a minute, what if there's all these other universes out there where things are different, but the fact that our universe eventually leads to stable planets, um, thriving stars, and life, and particularly intelligent life that can talk about the universe, maybe that restricts this range of possibilities down to one universe. And he called that the anthropic principle, for the Latin anthropos, which means people. So, the universe is just right for people. Um, Later, he and some others said, well, maybe that term is a little bit misleading because you don't just need people, you just need stability, stable planets and life. You could have
mhm.
other beings observe it. But anyway, that's one idea of the multiverse, is this idea of the anthropic principle, and it explains why you have a universe that supports habitable worlds.
And does the idea of the multiverse connect in any way to a potential theory of everything, or a simple unified explanation of the natural forces?
Well, this is what we call the holy grail of physics, or the
Yeah.
ultimate goal of physics, is to create a theory that unites all of the natural forces into
Mhm,
a single simple set of equations.
mhm,
And it's an elusive goal because we made great progress in the 1960s and 1970s with developing the Standard Model. And
mhm,
the Standard Model includes the electroweak unification, which very, very nicely unites electromagnetism with the weak force. The weak force is the force that explains radioactivity. And of course, electromagnetism explains why charges attract to repel and why magnets attract to repel. Well, all of those can be explained with a single theory that is also consistent with quantum physics, and it's very, very accurate. So electroweak predictions are as accurate as any experiment that's been ever been done. So it's extremely successful. Now we also have the strong nuclear force, which explains why atomic nuclei are stable.
Yeah.
And there's a theory for that called quantum chromodynamics, which is a very, very successful theory. And it's not as well tested, I should say, as electroweak, but it also has very similar properties to electroweak and involves this idea of two types of entities. One is the matter particles, quarks, electrons, and so forth. And then you have force carrying particles, which are particles that are conveyed from one particle, matter particle to another. So they're exchanged just like throwing a ball. Two matter particles throw, in a sense, a force carrier back and forth, and that creates a force. So you have a bunch of force carriers. You have photons, which carry electromagnetic force. You have the W particle and Z particles, which carry the weak force. And you have gluons, which carry the strong force. Now, in principle, we should have gravity should be described using a force carrying particle, which some people have called graviton. But no one has successfully developed a quantum theory of gravitation that is testable and describes, what we measure in the universe. There are a lot of ideas out there for quantum gravitation, and then the theory of everything would describe quantum gravity in a way that's consistent with all the other forces and unify all those into a quantum theory of all particles and all forces. And the leading candidate for that is string theory. But as I mentioned, string theory has all these possibilities, 10 to the 500 string geometries, and each of those creates its own theory of physics and leads to different parameters for the standard model. So those need to be significantly narrowed down to create a theory of everything. Where the multiverse comes into play is you can say, okay, there's all these possibilities out there. There's all these theories out there, but the theory of everything that happens to correspond to our universe was narrowed down by the fact that we're here using the anthropic principle. We can say, well, there are many, 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 many different theories of everything, but there's one that matches a universe that creates planets, that creates stars, creates intelligent life. And that's our particular theory of everything. And that's, why we have these particular parameters, different strengths of different constants. And that in theory narrows everything down to one universe and explains why we are living in this one universe and explains, all the constants for our universe. Well, we're very, very far from that. That's kind of an idealization. That's the goal, but no one has ever come up with a way to narrow everything down to one possibility.
But what are perhaps the main difficulties with integrating gravity with quantum physics? What are the bigger obstacles there?
Well, the biggest obstacle is mathematical.
Mhm.
So back in the 1940s, physicists such as Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga in Japan developed what are called renormalization methods in quantum electrodynamics. Now, that is a very technical term. but basically what that means is that you can take two electrons, which are basic charged particles, and you say, okay, let's develop a quantum theory of how these electrons interact with each other. And the way they interact with each other is by exchanging a light particle called a photon. And then you say, okay, you have an electron, gives off a photon. That photon is absorbed by another electron. And then that electron acquires a certain amount of energy, acquires a certain amount of momentum. And then you could predict the ways where the electron will end up. And that's called scattering. Scattering is when you have two particles, you predict, where they end up, what angles, what's the probability they'll end up at certain angles. And that's something you can physically measure, the scattering. You physically measure where these particles end up. You test it according to theory. And in the 1940s, quantum electrodynamics showed how you can add up all the possible ways electrons interact, and using something called Feynman diagrams, which is a neat way of adding up all the possibilities, and then using mathematical methods, get rid of infinite terms that pop up. So if you do these calculations with particles, because particles are infinitesimal, elementary particles are not only tiny, but they're believed in this theory to be, mathematically have zero size. So if you put that into the theory, you get infinite terms, because 1 divided by 0 is infinity, or unlimited. So during these calculations, before Feynman, Schwinger, and Tominaga, they found these infinite terms, but they were able to use a method called renormalization, which basically matches terms, subtracts them, so that you get rid of all the infinite terms, and that's renormalization. And when electroweak theory was developed in the 1960s and 1970s, it was shown that you could also match up terms, subtract them out, and then get a finite amount. And I use a nice analogy in my book about how renormalization works. I imagine a couple, two people, and they're living together, and one of them earns money and every week gets a paycheck, and she adds up all the money she earns throughout a lifetime, and she imagines that she lives indefinitely. It's just a hypothetical. So would make an infinite amount of money. And the other person is spending each month, and the spending would be infinite. And if you say, hey, wait a minute, this doesn't add up in the bookkeeping, infinite income, but an infinite amount of spending, that doesn't make any sense. But if you say, okay, every month, one person brings in the paycheck, another person spends it, and that creates a finite amount each month, so therefore everything matches up in the bookkeeping. So the accounting works out. Similarly, you can do a kind of accounting in particle physics with electromagnetism and the weak force, in which everything gives you a finite result. Well, it turns out with gravity, you try to do this and you can't match up the terms. You keep getting infinite answers. And the only way around it, as far as physicists can tell, is to say there's no such thing as infinitesimal, that every particle must have a finite size. And that leads to the idea of finite strands, which are known as strings, that vibrate instead of particles. So that leads to string theory. And string theory is finite, so you don't get infinite terms, but then you have all these possibilities for string theory, so you have to narrow things down. So that's the problem with string theory. You have so many options.
So earlier I've asked you about the Big Bang and the origins of our universe, but how about the future of our universe? What are perhaps the main hypotheses that physicists have proposed for the future of our universe? And is it that one of them has more support than the others? I mean, basically, what do we know at this point about the possible future of our universe?
Well, until the 1990s, I should say between the late 1920s or 1930s and 1990s,
Yeah.
the basic idea was that the universe had three options. One of them is that expands and then eventually collapses. And then the second possibility is that expands and the expansion slows down, but slows down very gradually and the expansion keeps going. And the third option was kind of in between the two, that the universe almost collapses, not quite collapses, and keeps slowing down, but never quite collapses. But then in 1998, these two teams of astronomers discovered using measurements of exploding stars or supernova that the universe is speeding up in its expansion. And that's called cosmic acceleration. And that means that you have a fourth option, which is that the universe will keep expanding forever. But not only that, but will speed up in its expansion. And eventually, just everything will just keep getting more and more dilute, and that galaxies will get further and further apart. And then finally, our set of galaxies will be a hermit, meaning like a loner in the universe, and we won't even see any other galaxies. We'll only see our galaxy and maybe a few others in the vicinity. And that is sometimes called a big whimper scenario, from the T.S. Eliot poem, that, how's the world ends, not with a bang, but with a whimper.
Mhm.
It's a line from a T.S. Eliot poem. But there's an even scarier possibility called the Big Rip. And that is that whatever is causing acceleration keeps getting stronger and stronger. And then eventually everything is ripped apart, including planets are torn apart, stars are torn apart, and even the atoms in people's bodies are torn apart. So everything is torn to shreds, and that will be the end of the universe. Now, those are some possibilities in the standard model of cosmology. But then if you believe in cyclic universes, believe in, for example, the idea of Steinhardt and Turek, that the universe is cyclical because you have two membranes, also known as brains, colliding with each other periodically and clashing with each other. There would be a periodic phase in which these two, it's like hyperplanes or planes in a higher dimension, collide with each other, wipe everything out, and reset the universe. And that would be the end of everything, but that would start a new phase of the universe. And then finally, there's Roger Penrose's idea, a different kind of cycle, where at the end of the universe, there's emptiness. Everything becomes more and more dilute. All the particles evaporate, and then eventually you have sheer emptiness. But that emptiness has a kind of identity crisis, mathematically, and instead of thinking of itself as very large, it thinks of itself as very small, and there's this mathematical transition, and then creates a new phase of the universe. So you have a new cycle. So those are some of the ideas about the end of time and, either destruction and recreation of the universe or just the destruction of the universe.
And is there, or I mean, what is the likelihood that wherever kind of scenario will occur, the universe will still be able to sustain life, and perhaps even worse, being able to sustain intelligent life like us.
Well, so we believe in the current standard cosmology that the universe is expanding faster and faster, and that
Mm,
but also that something called entropy, which is a measure of disorderly energy, is
yeah.
increasing. And that means that stars will eventually burn out and the sun will eventually die. Well, if
Mhm.
the sun dies, we imagine that maybe we have spaceships that take us to another star, but then that star might die. So then we go to a third star and we keep going. And maybe all the stars in our galaxy die. And maybe we have, you know, not only interstellar travel, but intergalactic travel. We try another galaxy. But eventually, all of these galaxies, stars will either, become uh, so cold they can't support life
Yeah.
or turn into black holes and so forth. So then the question is, can intelligent life survive? And that was answered at one point by Roger Penrose, who speculated that maybe we will develop ways to transform our uh, intelligence, our consciousness into maybe um, artificial intelligence or robots that could live in under very, very cold circumstances. But I'm not sure if that would be quite as satisfying to say that life would be in these robots that exist in ultra cold temperatures. It's not the kind of life that most people would want to live.
Yeah, for sure. And if a multiverse is real, would it have any bearing on the future of our own universe?
Well, if the cosmological multiverse is real,
Mhm.
um, unless there's some collision with another universe that happens to hit our part of the observable universe, probably it wouldn't affect us very much. We would just know that there are other universes out there that might have different fates than our universe. So might not affect us very much. Um, in terms of the quantum multiverse or the many worlds possibility, um, it's possible that we would have other versions of ourselves that might have slightly different fates in life. Um, if let's say during a quantum event um, that somehow affected the rest of our lives, it's unlikely that a single quantum observation will make a big difference in our lives, but it's hypothetically possible that by making a different observation, that could affect our lives and steer our lives on a different course.
And so, of course, in science fiction, many times people use the idea of time traveling and depict it in different ways in movies, books, etc. But is it theoretically possible, according to physics, for time traveling to exist or occur? And if so, would it connect in any way to the idea of the multiverse or not?
Well, when we talk about time travel, we need to distinguish between time travel into the future and
Hmm.
time travel into the past.
Sure.
Well, as Einstein showed in his special theory of relativity, if you take an astronaut, launch the astronaut into space, and that astronaut somehow can travel very, very close to the speed of light, and that astronaut returns to Earth, that astronaut's clock would tick more slowly than Earth clocks. And that astronaut could theoretically travel into the future of Earth. So, for example, if that astronaut was traveling 99.99% the speed of light, they might come back and see that all of their relatives are either 100 years old or likely deceased, you know, and Earth is, instead of being the 21st century and the 22nd century, because time is relative. So that is a relatively simple way to time travel, and that
Mhm.
doesn't create any contradictions, because you would just go into the future, you would arrive in the future, and you would maybe have different customs, and you know you would say, where are the smartphones, and they say, no, we use brain chips now, or we use something else. So you would say, oh, okay, technology has advanced. So that would be one way of time travel. But what about traveling to the past? We
Mhm.
imagine going back in time and trying to prevent the Second World War or something like that,
Yeah.
all these tragedies. Well, physics does have the possibility of that by creating something called a wormhole. Now, a wormhole, traversable wormhole, is a little bit like a black hole, only it's stabilized. So instead of having this um, very narrow uh, tunnel that possibly connects to another region of space that would not be uh, you cannot travel into, which would be deadly. We imagine being able to stabilize this tunnel and make it so that you can travel through it and end up in a different part of space. Well, as Kip Thorne and some of his students showed, there's a way that you can manipulate the wormhole so that it can act as a time machine, and you could travel backward in time, and um, and then uh, you wouldn't be able to travel before the creation of the wormhole, but you could travel back to at least the time when the wormhole was created. And so if there were wormholes that were created naturally in space that were useful as time machines, you could use one of those. And then the question is, could you affect history? And the way it connects with the multiverse is in science fiction, particularly, there's this idea that maybe if you go backward in time and you try to change history, that maybe you start a new branch of reality.
Yeah.
So, for example, let's say you go back in time to the age of Hitler and you assassinate Hitler, and there's no Hitler, there's no Nazi Germany, and World War II doesn't happen, but maybe something else happens. Maybe Stalin becomes all powerful and takes over Europe. And then, so now we have, instead of, Nazis trying to take over, you have a Europe that's run by Stalin and the Soviets. Okay, so that's a different branch of reality. Maybe that would represent, a type of multiverse where you have all these other alternative histories. But that is very science fiction-y, very
Mhm.
speculative. It's not something that physics can prove.
So another thing that perhaps is also speculative, you tell me, is the simulation hypothesis. So what is it, and does it have any relationship to the multiverse?
Well, the simulation hypothesis is the idea that could it be possible that everything we see, everything we observe is a computer simulation
Mhm.
that was designed by some other intelligent being? And the argument for that is, imagine our civilization, our own civilization evolves naturally. And currently, we have some forms of artificial intelligence, like we could create, at this point in time, you can create an essay that looks like it was written by a human being. It might have some mistakes, using ChatGPT or some other mechanism. Well, imagine um, that you could create a simulated human being, something that would be indistinguishable from a human being, And then you go on to create a simulated city where you have human beings interact, and it seems like human beings. And then you create a simulated planet, and then maybe a simulated, solar system, simulated galaxy. Well, if intelligent beings uh, last long enough, the chances, according to some thinkers, that they could create a simulation is 100%, that eventually they would develop the technology for this. So then imagine you have all these uh, natural worlds out there that create simulations. So you would have all these simulated worlds out there. Eventually, the simulated worlds would greatly outnumber the natural worlds, because you could have one natural world creating all these simulated worlds. So then you estimate the chances that we're in a simulated world or a natural world, and that becomes almost 100% according to these thinkers, that we're in a simulated world, not a natural world. So I don't quite buy that idea personally,
Yeah.
because there's all these other arguments about design, that we're designed, and the simplest one that people who are religious believe, well, maybe some people who are religious believe, well, we were designed by a divine being. Okay, well, some people don't believe that, some people do believe that, but it's a simpler belief to say that there's a divine being out there than to say, oh, well, there's another, set of beings that created us. Well, who created them? Were they a simulation? And it gets into this whole philosophical tangled argument about, why are there real beings? Why are there simulated beings? And what's the connection?
And if we actually were living in a simulation, would there be any way at all of verifying that, of empirically, I mean, being sure of that?
Well, I can only turn to science fiction and say, well, maybe someone would hand us a red pill and you take it, and all of a sudden you see everything like in the Matrix. Um, because if it was a really smart, intelligent being, they would create a perfect simulation. So, but you could speculate about intelligent being that's very, very, very smart, but makes mistakes and creates a flawed simulation. So all of a sudden, you wake up and you look up at the sky, and instead of seeing the moon or whatever, wake up at night, and instead of seeing the moon, you see something that looks like pixels, and you're like, hey, wait a minute, what are those pixels doing there? But if an intelligent race was smart enough to develop a simulation, it would conceivably be a perfect simulation, then you wouldn't be able to tell the difference. So this becomes almost like, you know, in a way, I think it gets a little silly,
Yeah.
a little comical, like, okay, if it's a perfect simulation, could there be flaws? Okay, that's gets a little bit silly to think about things like that.
Mhm. So we've been touching on science fiction here and there during our conversation, but what are probably some of the most common ways that in popular culture people portray the multiverse? And as a physicist, I mean, is it that you just take it lightly? I mean, it's just fiction, whatever, or is it that some of those ways that the multiverse is portrayed actually bother you?
Well, I think of it from the point of view of somebody who's a researcher, and they
Yeah.
apply to the government for a grant, or they apply to a corporation for a grant. So let's say they have this idea for testing, using observations of the cosmic microwave background to test for other universes. And the word multiverse comes up, and they send it to somebody to review their grants. And that person has just seen a Marvel movie. Just saw Doctor Strange in the Multiverse of Madness. and they come back and say, this is not real science, this is science fiction. You don't get any money from me. Or it's another possibility. You could have someone who says, wow, I love that movie. I love science fiction. That's really cool that you can test these things in real life. You get, here's $100,000, for your grant, 100,000 euros. So then you could be lucky. So it's a little bit of a mixed thing. Some scientists are like, well, science fiction talks about multiverse ideas. Those are really not real science. So let's not even talk about a multiverse. And others appreciate the popular interest as a way of supporting science. Like, okay, you've seen the multiverse in movies. Let me show you the real multiverse ideas. Forget about the movies. Here's the real science of it. So in the movies, the main attraction is the idea of what if. What if, Spider-Man came from a different background?
Yeah.
What if, in Star Trek, instead of Spock being logical and emotionless, what if Spock were evil and very emotional? So we see, an alternate universe where Spock has a beard and is sinister and so forth. So these are all talked about in science fiction. And then there's even the simple question, what if I missed a train instead of making a train? And that's the movie Sliding Doors, where a woman just misses a subway train versus just makes a subway train. And the movie shows what happens to her life in the world where she just makes the train, and another possibility where she just misses the train. And in one of them, she discovers that her boyfriend is having an affair with another woman, and she breaks up with the boyfriend. She finds another boyfriend who's much nicer, and her life continues. And then in the other scenario, she doesn't discover that her boyfriend is cheating on her. She continues with the same boyfriend. And then we see what happens at the end. And I'm not going to give too much away, but the branch of reality, which looks like a good one, might not be so good after all in the movie. So these are intriguing ways to think about the multiverse in science fiction.
I mean, it's as if every time in movies, every time people think about different possibilities, they're dealing with counterfactuals in their mind. What if this happened? What if that happened? Reality branched, and then a new universe popped up where the what if really happened, right?
Yes, that's right. So we often imagine what would happen if we made different decisions in our lives. Like, what if we decided to move to a different city?
Yeah.
So, what if we decided a different job? So imagine we grew up, and as a teenager, we were in a rock band, and we played it at our high school, and everybody applauded. And then our parents say, "Wait a minute, you can't make any money from a rock music. You should go into a serious job," and we become an accountant instead. But then we imagine what would be a scenario where we say to our parents, no, 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 we want to just stay in music. And then we become the Beatles or the Rolling Stones or another very successful rock band. We say, it's very good that we didn't listen to our parents, and we pursued our musical dream because we became one of the most successful bands of all time. So we don't know unless there were, the possibility of viewing other universes, other branches of reality, we wouldn't know if our decisions were good decisions or bad decisions.
So one last question, and then sort of related to this previous one. Do you see, I mean, how do you look at the popular ideas that people have about the universe? Do you think that they attribute specific meanings to the universe, to the multiverse, that it might be meaningful in some way for people to consider the possibility of a multiverse existing?
Well, I think it's fun to imagine about different things.
Mhm.
And I like science fiction personally, and I like dreaming about other worlds and thinking about different scenarios. And I think that's perfectly healthy. The only time I have a bit of an objection is when people exploit quantum physics or exploit the idea of a multiverse and try to convince people that they can control their own reality by using quantum physics. So they'll say something like all you have to do is want to be rich and um, you know, buy my book or listen to my audio. I'll show you how. So it's only $100 for this audio, and you'll learn how that using quantum physics, you'll use your mind and make the right choice, and that will propel you into a universe where you're very wealthy using, the idea of a multiverse. Well, somebody is making money from a false premise there, but
Yeah.
it's very easy to try to exploit physics and to try to convince people uh, that they can use it to become rich or become, immortal, become, super healthy and so forth. So personally, I would steer away from those ideas because it's not really a proper use of physics to say, if you think you're rich, you're going to be rich.
It's like that very popular book from a few years ago, The Secret, right? And other
Yeah.
similar ideas popularized by some self-help gurus, right?
Yes, although there are people who find quantum books in the self-help section of a bookstore and then become seriously interested in real scientific ideas. Like, for example, um, uh, I know a rock musician who in the 1990s looked at a lot of self-help books, and that led him to write songs about quantum physics. So it can be a good thing.
Well, let's end on that note then. And the book is again The Allure of the Multiverse, Extra Dimensions, Other Worlds, and Parallel Universes. I'm leaving a link to it in the description of the interview. And Paul, just before we go, apart from the book, would you like to let people know where they can find you and your work on the internet?
Well, I'm active on what used to be known as Twitter, also known as X.
Yeah.
I'm also on Blue Sky, Mastodon. I have my own blog, uh, and that's active sometimes. I post things and I post articles. So if you Google my name, some of these things should come up, social media. There's a Facebook writing page for me, but I'm not involved in that, but there are a lot of social media that you can reach out to me, and especially on X, Twitter. I'm very active on that under the handle P. Halpern.
Great. So I'm also leaving that in the description of the interview. And thank you so much again for taking the time to come on the show. It's been fun to talk with you.
Thank you, Ricardo. Those are wonderful questions, and I really enjoy the interview.
Hi guys, thank you for watching this interview until the end. If you liked it, please share it, leave a like and hit the subscription button. This show is brought to you by Enlights, learning and development done differently. Check their website at enlights.com, and also please consider supporting the show on Patreon or PayPal. I would also like to give a huge thank you to my main patrons and PayPal supporters: Per Ergo Larsen, Jerry Mullerens, Frederick Sunda, Bernardo Seixas, Olaf Alex, Adam Kessel, Matthew Whittingbird, Arno Wolf, Tim Hollis, Eric Alenia, John Connors, Philip Forrest Connolly, Dan Demetri, Robert Windiger, Rui Inácio, Zup, Marco Neves, Colin Holbrook, Phil Kavanagh, Michael Stormir, Samuel André, Francis Forte, Tiago Nunes, Fergal Cossen, Hal Herzog, Nuno Machado, Jonathan Librant, João Linhares, Stantantia, Samuel Correia, Eric Hines, Mark Smith, João Eira, Tom Hummel, Sardas France, David Sloan Wilson, Yacila Dez Araújo, Romain Roach, Diego Londonho Correia, Yannick Punter, Adana Rusmani, Charlotte Bliss, Nicole Barbaro, Adam Hunt, Pavlo Stasevski, Nelek Bach, Guy Madison, Gary G. Alman, Sam Afzal, Adrian Yeager, Paul Tolentino, João Barbosa, Julian Price, Edward Hall, Edin Bronner, Douglas Fry, Franca Bortolotti, Gabriel Ponce Cortez, Ursula Litsky, Scott, Zachary Fish, Tim Duffy, Sonny Smith, John Wiseman, Daniel Friedman, William Buckner, Paul George Arnaud, Luke Loaki, Georgios Theophanes, Chris Williamson, Peter Wolozin, David Williams, Diogo Costa, Anton Erickson, Charles Murray, Alex Shaw, Maury Martinez, Coralie Chevalier, Bangalore Atheists, Larry Dealey Jr., Old Erringbone, Sterry, Michael Bailey, Dan Sperber, Robert Grassi, Igor N., Jeff McMahon, Jake Zool, Barnabas Radix, Mark Campbell, Thomas Dovner, Luke Nissen, Chris Story, Kimberly Johnson, Benjamin Galbert, Jessica Nowicki, Linda Brandon, Nicholas Carlson, Ismail Benzliman, George Coriatis, Valentin Steinman, Per Crowley, Kate Van Goller, Alexander Hubbard, Liam Dunaway, BR, Masood Ali Mohammadi, Perpendicular, Jonas Hertner, Ursula Goodenough, Gregory Hastings, David Pinsoff, Sean Nelson, Mike Lavigne, and Dios Necht. A special thanks to my producers, Isar Webb, Jim Frank, Lucas Stafiniak, Tom Vanagdam, Bernard Igni, Curtis Dixon, Benedict Mueller, Thomas Trumbull, Catherine and Patrick Tobin, Giancarlo Montenegro, Alnick Ortiz, and Nick Golden, and to my executive producers, Matthew Lavender, Sergio Quadriano, Bogdan Kanivets, and Rosie. Thank you for all.